Hello everyone, good morning. So now we start with a new topic that is constraint satisfaction problem in AI. So let's go started. Now we have reached a certain landmark point in a course because up until now we have been talking about search algorithm. We have said that AI is a search. We have said that AI can be thought of problem solving. You would be given a new problem, and whenever you are given a new problem, you will define a general purpose problem definition version of that problem. And that general purpose definition was the atomic agent definition, where we are given a set of states, but we are only given a starting set, a successive function, and a goal. One player, two player doesn't matter. In case of two player, whether we know we win, lose, or a draw. And this formulation sort of works in a large number of problem solving scenarios. One of the assumptions that the atomic agent made is that a state is indivisible. Now, I would point out that this is not always how we went ahead and we relaxed some of those ideas like. For example, we talked about domain relaxation. Now, we can only talk about domain relaxation if you know what is inside a state, because then we know what is happening in the domain. We relax it and then we can compute the heuristic function. So it is not that we always thought state to be a number which we cannot go inside, but we did not have any canonical representation or canonical way to represent the state. This way of representing the state was in our head, which was problem specific. And then we create those extremely general purpose algorithms, which whether the state is number or we have a more structure on the state of whatever it will still work. And we did a lot of search algorithm, batch first algorithm, depth first search algorithm, iterative deepening search algorithm, A stars algorithm, and local search formulation. We did min-max in the constant of the game theory, and this is the AI is such a mindset. Everything in AI is a search. So whatever problem you come up with, we will create a search, and log of that I will able to use some existing algorithm to solve it. Now we move to from AI is search to AI is a representation, and this is our next big mindset. So what are the topic we are going to cover in this module is a introduction, a representation of the atomic state. We are going to define the DSP, that is constraint search problem. There is a mistake. It is CSP, constraint satisfaction problem. Then we are going to see what are the examples different. Backtracking search for the CSP, that is constraint satisfaction problems. Then we see problem structure, problem decomposition, and the local search for the constraint search problems. So first we see the introduction of it. AI is a representation that great mindset to have, especially if our goal is to solve many problems at the same time. And the reason is that the atomic search paradigm, atomic agent paradigm, we do not know anything about the state. We cannot go inside the state. We cannot say that this state is sort of very similar to the state, only something has changed. For example, if my question is whether it is going to rain in a Delhi today or not, and you know my state, I also know whether it is rain in a New York today or not. I can say that it doesn't matter. Let New York rain today, or let New York not rain today. Who cares from context of the Delhi? So therefore, there will have same probability of those two states. All such possible reasoning and interference are possible only when we are allowed to look inside the state. So now for the purpose of n queen problem, you can say a queen is location at 1, queen is located at location 2, and it is my state for the purpose of the puzzle. But notice that different kinds of problem will have a different state of representation, and that is not in a good, because if everything has a different representation, then it creates a problem. So we cannot do anything general purpose. So the goal of AI is come up with general purpose representation, extremely general purpose, which allow you to represent your problem in representation effectively. Let's consider uh, there is a brain, and how this is a part of inside the brain which goes problem solving. It runs the min-max algorithm, it runs the star algorithm, it runs all those algorithms. That is a core of AI, because every problem that needs to be solved may require some search or may require some other algorithm, a general purpose algorithm. And those are general purpose algorithm. Now, how I tell you my problem to the brain. How do you human take the problem to the human? They use the word, the language. How do we communicate it with computer language? You write the program in C++ or Python or any other programming language. It is a language that we understand, computer understand, and it is a common language between the computer and the human. Now, up till now, how we have been specify the problem to the machine. We have been saying that I will give you a goal test, I will have a successive function, I will have an initial state, which is a number, and all those things will give a you code as a binary or as a function. Now, this is not a language, this is a pre-pseudical view where my machine can make an API, or call my machine can make a system call. And this is a goal or no. And the goal test will represent the answer yes or no. One may have even know the actual problem. It doesn't matter to from where the from the where the problem is come. What is the purpose of the problem? For the brain. The brain is simply learning that algorithm and making those tests and successive function and finally giving you the result. But let us say we want to give the problem to the brain. Let us say we want to do more interesting interference. So in that situation, you will have a problem solving component in the middle. But let us say we want to write down a problem to the brain, not giving it as a code. In a such situation, we need to come up with a language which human can have a problem in mind. He or she writes down this problem in a given representation. So the machine and the human both understand this representation, and then this representation goes into the brain. Now brain can obviously run the basic atomic agent problem, solving the scenario, and it could say you are giving me a problem in a language 1. I will use the properties of language 1 to understand something about the new problem in the new domain and actually reduce the search. You can always use the basic search, but this search will never scale for you, but if you are given a specific representation, a specific language, and you will able to use the properties of this language, you might able to save your time, remove the parts of the search, and make it faster and much more scalable. Therefore, there are some people who believes that AI is a representation, AI is a thinking about in what language should the problem be given to the machine, and in using those property of the language, we can reduce the amount of effort I need to do as a machine to solve the problem. We will fix that problem by three examples of this. I hope by end of those three examples, you will have some intuition of what I mean and what I say using the properties of the representation. To reduce the total search space, what are three representations what we are going to study in the AI course? We'll study the representation of the constraint satisfaction problem. It is very simple representation. The most interesting representation that we are going to study is proposition logic. Now, that is the next module. We are not sure whether we cover in this semester or not. Now, you will also know the Boolean logic. It is very similar, but we will see what more we can do with the Boolean logic. By the way, logic is used to be a de facto standard for the presenting new problem in the AI from last 30 years or maybe a 40 years, right up to the 90s. Logic or variant of the logic are used to define the problem. In the later part of AI, probability started to come in, and so we will learn one representation of the probabilistic AI, and that will be a Bayesian network. So there are three next steps that we are going to have in the syllabus in the pipeline is constraint satisfaction problem, pro- propositional logic, and Bayes network. And in all case, we'll know how to look inside the state. As among those three, we might end our this semester with constraint satisfaction problem. The next two parts, the logic and the Bayes network, will do in the later. So now we're defining a constraint satisfaction problem. A constraint satisfaction problem consists of the three components x, d, and c, where x is a set of variable from x1 to xn, d is a set of domain from d1 to dn, one for each variable. So each variable has some of the domain from the d set, and c is a set of constraints that specify allowable combination of the value. Each domain di considers set of allowable value from v1 to vk for variable xi. Each constraint ci consists a pair of scope and relation, where scope is a tuple of the variable that to be participate in the constraint, and the relation that defines the value that those variable can take on. A relation can be represented as the explicit list of all tuples of the value that satisfy the constraint, or in the abstract relation that suppose two operations. Testing if a tuple is a member of the relation and enumerating the member of the relation. For example, x1 and x2 both have a domain A and B. Then a constraint saying the two variable must have a different value can be written as x1, x2 has A, B or B, A. Or we can say x1 and x2 where x1 does not equal to x2. To solve the constraint satisfaction problem, we need to define the state space and the notion of the solution. Each state is CSP, that is constraint satisfaction problem, defined by an assignment of a values to some or all the variable from xi to xj with a value vi to vj. An assignment that does not violate any constraint is called constraint or legal assignment. A complete assignment is one in which every variable is assigned and a solution of constraint satisfaction problem is consistent. Complete. A partial assignment is one that assigns a value to only some of the variables. This is how we define the constraint satisfaction problem in more about constraint satisfaction problem. A constraint satisfaction problem is one of the standard search problem where instead of saying that state is a black box, we can say that a state is defined by variable and values. It is extremely simple, like in case of all u is very well known about the variable. Let us say we talked about n queen can be think as a variable value problem. Each variable would be a variable I would be the queen position of the ith column and its value will be the position. If you think about n puzzles problem, you can again say the type position is a variable and its value is actual position. So now if you think about it, most of the problem or many problem are can be defined with the variables and the value. You will able to cast where you have where you say that each state each state has a certain state of the variable and each variable has certain state of value and a complete assignment to all the variable creates the final state or a word state. If we are doing a local search, we are doing a local search in the word state. But if we are doing a systematic search where we are adding one variable at a time, my node would be a partial assignment. So, as the slide says, this is a simple example of formal representation language in the field that which we are getting earlier. It allows for general purpose algorithm with more power than an atomic agent. That is very important because in atomic agent there was only a state with only a number. There is only so much we can do now that a state is more than a number. It is a set of variables and a value. We can do more as we can understand the structure of the state and perform the better in our task. Now we'll move to the example of first example of map coloring. So the particular set of slides we will carefully look at the map of Australia. We will try to solve the graph coloring problem or a map coloring problem. So first of all, it will help to memorize this. We have 7 states in the Australia. Western Australia, Northern Territory on the top, Southern Australia in the middle on the south, and then we have a Queensland, New South Wales, Victoria, and Tasmania as island. And those you have a sort of memorize. It will have to memorize because we will use this example many a time. Now let us say we have to assign a 3 color to this, that is red color, blue color, and green color that we wanted to color. So if I say assign a variable x variable to this state, then the variable will be WA, that is Western Australia, NT, Northern Territory, SA, South Australia, Q, Queensland, New South Wales, NSW, Victoria, and Tasmania Island. These are my variables. Now I will define my domain, that is D. So my domain will be I have to do the color. So it will be a red color, green color, or a blue color. There is a 3 set of color which we have to assign them. And then we are talking about the constraint problem. Now the constraint to this map coloring problem is that the adjacent region must have a different color. So we can say the adjacent region must have of a different color. Or example, I can say that WA, color of WA should not be equal to NT. This is one of the example we can give. Similarly, you can give any other example or another way of representation of the constraint. So there are multiple ways you can represent a constraint. So two adjacent state have should not have the same color. So this is very standard graph theory problem. If we wanted to pass into the constraint satisfaction problem, our variable would be a 7 variable, and that variable we have defined. So, and each variable is assigned with each domain. As we have seen that each variable should assign to the one of the domain. So every variable is assigned with one of the color. And then we will see the constraint that two adjacent cannot have the same color. While the adjacent to each other in the map cannot have the same color, now do we represent this constraint is also interesting. You can represent this constraint with a simple inequality or in another language which is allowed to you. We have not really defined a constraint language, and a different people study a different state of constraint language, and this is a new area is called a constraint processing, and which is an active area of the research nowadays to define only how to define the constraint, that is constraint language. But you may say that not equal is not part of my language, but a numering the state of possibility is a part of my language. I can say that my language can use or say that a Western Australia common North reality can take the value from the red blue, or green red, some kind of the combination. This is another way of representation of the language. So if we assign these all these things, we come up with the this map coloring problem. So you can see no adjacent cell has map as same color. So finally, the solution set of this constraint. So you can write the solution set will be that North Australia is red color. Similarly, North Territory has a green color, and so on. You can write with Tasmania T as a green color, and so on. We can write all 7 states with that different color. This is one possible solution of the problem you know. You label a color, okay, and they may a multiple solution assigned. A solution is a specific assignment to each variable and such that all constraints are satisfied. That is what we talk about the solution. Now we'll see what is a constraint graph. So this is what we can say it is representation as a graph form. Now, often people in a constraint processing think of constraint graph. In a constraint graph, each node is a variable and each edge determine whether there is a constraint between those two variables or no. So you can see these all are the variables, and whenever there is a link, it is a constraint. So whenever there is a constraint, we will draw the link. So you can see Tasmania has no constraint with anyone because it is not adjacent to any of the state. But you can say Western Australia is a constraint with North Territory and the South Australia. So this is kind of a constraint graph, or we can say binary constraint graph, where each constraint related at most two variable, and such constraint satisfaction problem are called the binary constraint satisfaction problem. This is very, very important. You may say binary CSP to say specific because each constraint is only between two variables. But in fact, you can prove or you can there are procedures which can convert a non-binary discrete CSP into a binary CSP. So just we can think about studying binary constraint satisfaction problem and no worry about others. Of course, there is some lots of new variable need to be created, etc. When you convert from non-binary CSP to binary CSP. If anything, we will talk about converting them into the binary CSP because that is all about the algorithm that you will study. We will about the constraint which are between the two variable only. And the good general purpose search algorithm might quickly find that there are two sub problems in the problem. And what are two sub problems? And whatever two sub problems are there, and are there two independent sub problems, or there are a connected component to each other. Let's say, as we discussed, Tasmania is a different component of the six different uh, states. So it is really doesn't matter how we label, just purpose of labeling a rest of the graph. So we can actually convert into two independent problems, solve each of those problems separately. So from this graph, you can see whatever is not connected with any graph, we can solve these problems separately and we can solve these problems separately. So we can just separate two independent problems and do solve them separately. This this would only be able to do if we look at the constraint graph or something understand from the structure of the problem. Now we can think about structure of the problem because each state variable is a node, not a state. And I hope you see that is a difference. Earlier, each state was a node. Now, each state has a many variable. And let us call those state variable as a node. So, we are operating in the world of the state variable at this point, not in the world of the state only where we are able to recognize that there are two independent sub problems. Now, we'll talk about varieties of constraint search problem. The constraint search problem is come with many varieties, and there are constraint search problem with a finite dimension, discrete variable, and there are CSP with an infinite dimension, discrete variable, like integer or a string as a solution. There can be CSP with a continuous variable. For many common world, real world problem are constraint satisfaction problem like job scheduling, or there are many kind of problems which are a continuous problem. So I want to satisfy, I want to finish a job up to a certain days before end time, you know, it is a constraint satisfaction problem. Suppose I have a discrete constraint satisfaction problem and I have a no variable, and each variable has a value which can be taken from the domain size D. Then how many complete assignment do I have? D to the n. The first variable can take D value. The second variable take the D value. The nth variable take the D value. So we will have D to the power n complete assignment. So if we would enumerate all the data D to the power n assignment, then of course we will able to solve the problem really. But of course that is not possible because it is exponential series. Now we'll see some another varieties about the constraint. So different people study many different kinds of constraint that do not label South Australia as a green color. This is one constraint added. Other than what we have a constraint that two adjacent state does not have a same color. And another constraint is added that South Australia does not have a green color. Maybe reason that it does not have so much greenery or whatever is the reason. But let us say there is a constraint we said do not label South Australia as a green. Then that will be presented not equal to green. And then you have a binary problem and then you have a unarray construction. you will have a binary constraint where you know that South Africa should not equal to the Western Australia, and you will have a higher constraint like 3 or 4 variable come together and they define a constraint. You may have called some soft constraint. Now, what is soft constraint? A soft constraint need not to be satisfied, but you get the credit for satisfying them. So this is actually will not give much pressure when you deal with the soft constraint problem. You do not always satisfy them, but you know you are happy to satisfy them because once you satisfy the software constraint in your problem, then you convert the constraint satisfaction problem into a constraint optimization problem because you are trying to optimize by gaining more credit, more values. Because now I have some constraint, I need to satisfy them. I have some constraint, I may not have to satisfy them. But satisfying each constraint will give some credit. So I need to get maximum credit by satisfying all constraints, and this all constraint, then we can say it is a constraint optimization problem because of the maximum part. Now we'll see one more example of cryptarithmetic. This is what you have seen in a kind of cryptography. Okay, so many interesting problem that you study in your real life can be thought as a constraint satisfaction problem. This is something like a cryptographic puzzles. What if I give you 2 plus 2 is equal to 4, where each symbol, each letter means a digit and a different digit such that this particular sum is accurately satisfy the variable TWOFUR. But you realize I want to actually put it as a constant. I will have to define 3 more variables. Okay, so before that, we will just first try to write down the variable from this, what we can say. So we can say variable, or we can say x. So what are the variable? T, W, O, F, U, R. And other than that, we are all specifying a 3 more variable, which is x1, x2, and x3. Which, and what will be that? That all these numbers should be from the domain 0 to 9. So another variable we define to define the constraint, that is x1, x2, and x3, and the domain will be from 0, 1, 2, 3, 4, 5 till 9. So this all variable take the value from 0 to 9 only. Now we will see a constraint. The first constraint we can say all, this is all different. What is meaning by all different? That the value which is assigned to this, that is T, W, O, F, U, R, will be a different value. It means this, and none of the values should be the common. Okay, this is a one way of defining a constraint. Another constraint will be that O, I just write it down as O plus O will be equal to R plus 10 times of x1. So that is O plus O equal to R plus 10 times of x1. This is one of. Similarly, there are many constraints you can add to this with your x2 and x3 variable. So this is what the constraint. Another set of constraints that we have seen, the different digits you assign the different variable. Okay, and this is written as a syntactic dual way, that is all different. That is you have to remember. So everybody was told about those different, and that is the constraint graph for it. Notice that now we have created those 12 nodes which represent the constraint, and multiple edges from the variable can be used in each constraint. But of course, we can always convert into the binary DSP. So this problem again here we can say it is converted into the binary DSP, which will give you the value of FTURWO from the constraint C1, C2, and C3. Now we move to the next part, and we will just not much talk about the in details of the real world constraint problem, but we just see what are the real world constraint problems are there. So let me end the introduction here, and we'll just see what are the real world constraint search problems. Our assignment problem, that who teaches in what class, or time labeling problems like what when we are using a making a timetable for the university or college, that which class is offered to when and where. There are some hardware configuration problem, spreadsheet problem, transposition scheduling problem, factory scheduling, that is a job scheduling problem, floor planning. All those problems are part of the constraint satisfaction problems in the real world.